Welcome everybody to the fifth module of the series of cloud-enabled research workshops organized by Microsoft Fabric and Azure AI for academic research workflows. Today's session will talk about experimental design and machine learning for research. If you have followed the previous modules in the series, you will be familiar with the host, which also today is Marco Pilia, and I hope I'm not butchering the surname here, and it's not too far from the correct pronunciation, who is a Microsoft certified trainer from Algebra Bernays University. And of course, I will leave the word to the expert now. And so without further ado, I'll pass the word to Mario.
Thank you very much, Leonardo. I welcome everybody to our last module of this series. As been said, experimental design in machine learning for research. Let's just, for the ones of you who does not know me, a few sentences about me. I come from Croatia, in general, Zagreb capital, but currently located on a beautiful seaside, enjoying some kind of balance in work and summer, seaside and stuff like this. But important stuff, I'm more than 16 years in IT industry, been in many roles from solution architect, AI engineer. Obviously, I'm Microsoft certified trainer. I have many more certificates from this background. And these days, I'm focused on some kind of AI flows, AI workloads, AI integrating in the business processes, etc., etc. So, without further ado, let's just quick chat what we have covered in last sessions. So, this is our fifth session. This is our fifth model. We started with research paradigms, with playing around in introduction about Microsoft Fabric, some kind of terms like one lake house, medallion architectures, FAIR principles, data, building up data agents. In second session, we went in the data engineering, talked about different kinds of other aspects of technologies in the Azure landscape, which can help us here. Moving forward to the AI workflows, where we introduced AI Foundry. You will see lots of similarities today with this portal. Talked about prompt engineering, RAG, grounding, AI agents, code interpreter in general. And in our last session, we've been exploring the other AI services in Azure for text analytics, natural language processing, knowledge mining, AI search indexing, document intelligence, lots of stuff. So today we are going to go deeper. We are going to check the machine learning foundation. We are going to talk about how to design, track, deploy machine learning experiments for research. How are we going, what kind of support do we have with technologies in the Azure about that? So we are going to dig deeper in it. This is some kind of agenda for 2 hours of our hanging time together, from machine learning experiment lifecycle, distributed confidential machine learning, model deployment for research, architecture, machine learning research lab. We are going to show a couple of demonstrations. I'm going to navigate you through this machine learning studio to see what you can expect there and what kind of features does this technology have. And all this is going to be wrapped up to some kind of connection to the previous modules and just giving you additional materials, additional links for the next steps, etc., etc., etc. So let's start it. What's the problem in general in machine learning experiments? Models are in many cases, I would not say most, I would not do this bold statement, but in many cases trained on the laptops, on the local machines. Data scientists are doing some kind of experiments with no version control of data, no kind of version controlling of the code parameters. It's hard to share these kinds of stuff. Results cannot be reproduced even by the same researcher or a month later. There is no systematic comparison of different kinds of experiments, even models of some kind of standardization. In some cases, you probably heard the sentence, I tried a few things and this seems the best. There's no audit for ethical boards, founders, peer reviewers. There's no path from experiment to deployment. Model stays in notebooks forever, Jupyter notebooks, some kind of Python code that is locally on your machine. And when you have compute intensive training, you are limited to some kind of local setups, like maybe some local machine or some kind of local clusters that needs to be then managed, that needs to be then set up in some kind of networking, patching. You are dealing with lots of stuff of providing this kind of infrastructure. Let's just think about, we already spoke before the starting of the session of this some kind of water quality of fictive scenarios that we are covering through all those models, but let's just think about it from the perspective of some kind of fictive person, Dr. Elena, who is environmental scientist, and she needs to have experiment tracking, hyperparameter tuning. She needs to have some kind of responsible AI, deployment, reproducibility. This is something that she, from this kind of research scenario, she demands. She said that she has 6 years of water quality data from monitoring of 8 sites across 4 countries. She needs to predict dissolved oxygen levels from other parameters to identify sites at risk. And she has been doing this in Excel with linear regression. She needs to, compare different kinds of algorithms, different kinds of approaches systematically. And she wants her ethic boards to have full audit of every model decision. It's important stuff. And this is the exact problem that Azure Machine Learning solves. And we are going to explore how. Okay, Azure Machine Learning as a researcher lab, let's dig deeper in it. When we are in Azure, you have opportunity to provision different kinds of resources. We saw in our last sessions many kinds of different kinds of AI services, AI Foundry, Fabric. Machine learning service is just one type of particular Azure resource that can help us here. This is the top level resource for all machine learning work. You have opportunity here to track every experiment, have an overview of all your models, data sets, compute targets. When you're talking about compute, we're talking about hardware, we are talking about compute instances in a background, automatic versioning of all assets. You have built-in collaboration. You can share those experiments, share those findings across the team, limit some with permissions. You have connected services like storage. You already are familiar with storage. We are keeping some kind of data, some kind of learning, some kind of observation data, our data sets over there. Key vault for storing secrets, for storing some kind of keys, for storing some kind of secrets in general. Container registry for deployment of our models in containers, where we are going to pull up the images. Application insights for fully monitoring how things are working and to have completely observability. So we have multiple different kinds of ways how to approach to machine learning services. We have SDK on a different kinds of programming languages. We have CLI, so you can play around with the Bash or PowerShell or command line. SDK from the different kinds of perspective of programming languages. And obviously, what you will see today, we have Machine Learning Studio. It's a web application. It's a studio portal where you can manage all those stuff through the user interface. There's different kinds of components under the machine learning workspace. We have experiments, which track runs, parameters, metrics. We have models where we can register model, we can versionize model, we can deploy the model so we can consume them afterwards. We have data assets where we are connecting to some kind of data stores, compute. Those are hardware, compute instances, clusters of our machines that are going to do this hard work for us. We are in control here, deciding of the disk, CPU, even GPU. We have all those stuff. It's something that we can fine tune and we can regulate stuff. And we are the one who are then able to build up those clusters that will serve for our training of the models, then put them down, etc., etc., etc. We have several options. We're going to talk about it. Environments, those are reproducible runtime configs, endpoints, real-time batch inference. What does it mean? Once when you have the model, you have opportunity to bring this model live. That means that this model will then be served as a standalone container and can then be used. Machine learning services gives you opportunity to have this infrastructure in a background, which can then be used for the hosting of this model. Then you can consume your model through the real-time or batch endpoints. Pipelines, which you will see today, we have some kind of automated machine learning workflows. Lots of stuff that you can play around with it here. Okay, so let's do some kind of parallel with the Foundry, which we observed in last sessions. So workspace architecture in general is the same as in Foundry. We have Hub, which is centrally managed security, networking, compute quotas. We have project. We have individual workspace for each research team or study. You can organize your work like that. You have the same model as a Foundry, where Hub is research group, project is a study. You have different kinds of connected services, storage, key vault, container registry. You have, which is really important for the governance perspective, data isolation between projects with the same hub. And IT admin can set it up, hub as once, researchers underneath create projects as a self-service and organizations. So this is just some kind of parallel with the knowledge that you already have from the previous modules. Let's talk about compute targets. So once when we set up our project, our hub and everything, important stuff is to realize that nothing is going to happen if we don't have some kind of hardware in a background, which we can use in our experiments, in our workflows. Those are the options. You can provision compute instance. This is your personal cloud workstation. What does it mean? Through the studio or through the CLI or SDK, you are then consuming this instance for yourself, where you can then apply and install your notebooks. You do this for exploration, debugging. You do your stuff that you are used to do it on your local laptops, your local machines, local workloads. You have on those compute instance pre-installed machine learning frameworks. This is speeding you up. You don't need to do any kind of additional pre-installations. Those instances are, going live with lots of the stuff predefined for you, so you can dig into your work immediately. And you're paying those only when it's running, which is important stuff. Once when you are done with the consumption, with the consuming, with your experiments, with your exploration, you just, stop it. And when you want to do it again, you just bring it live with a once click of the mice. And you are charged only when you are live and you're consuming this. On the other hand, you have compute cluster. What does it mean? That means that you have opportunity to have machine learning services are taking care of scaling of lots of the different kinds of instances in the background. Why? For training jobs, because lots of the different kinds of work are not so easily to be done on one machine. You have opportunity with the frameworks and with cluster to parallelize work to do on the massive scale of data, which is the real deal. You have multiple nodes for distributed training. You are scaling to zero when it's idle. But auto scaling means that you have multiple instances depending on the heaviness of the job. If there is no job, it's going to auto scale to zero, so you're not consuming anything that is you're not provisioning or having anything that you're not consuming. You're submitting jobs and you can just walk away. You're just pushing some kind of job that is going to last for, I don't know, 20 minutes, half an hour, 2, 3 hours. And you have opportunity to track the progress of the job through all those three channels, SDK, CLI, or through the portal. And it's cost efficient for the batch work. Serverless, third option, you are not taking care of any kind of management of the cluster. So everything is done by the Azure itself. Azure allocates resources on the demand. It's ideal for occasional experiments. So Azure is going to calculate how many compute do you need to have. Depending on the heaviness of the job, it's going to automatically scale up or scale down, regarding the heaviness of the job. You're paying per job, not per hour. So you're just leaving something to be done in some experiment. So this is the simple path to get started. You are not then messing around with any kind of additional infrastructure administration. You're just leaving the serverless for computing. If you think that you are limited only to some kind of laptop, or let's say it on-prem or the cloud solution, you're not, you can have distributed compute. You can have laptop to cluster journey. So researchers often outgrows the single machine on the terms of demands. Azure machine learning clusters are scaling from 0 to n nodes automatically. Is the same model as a Spark in a Fabric. You remember the Fabric where we examine this kind of stuff. You have GPU clusters for deep learning workloads, really important stuff. You're not only limited to the CPU. Serverless, Azure manage everything, not just you just submit jobs, as we said. You have cost control, where you set up the max total trials timeout, auto shutdown, and researchers never wait to compute. You just submit and go. So your process stuff through the different kinds of aspects there, and you are consuming this large amount of possibilities and compute power from the Azure for your jobs. Let's explore two other, I would say, terms, topics here. Let's talk about data assets and environments in the details. What are data assets? Those are some kind of data stores, connection to the Azure storage databases, OneLake, whatever, where your data is. You can push it everywhere. You can upload it from your local machines. You can point it to existing services like storage, as has been said. That's important stuff. Without data, there is no experiments. There is no any kind of jobs. Data is completely necessary. So you have their data assets. Those are the version references to specific files or folders. You have some kind of URI references. You will see in the demo that I will show you that we have this particular stuff. We have reference with the URI to the blob storage. ML table, which is typed schema aware tabular data format. You have native integration with Fabric, one lake shortcuts data sources. Every data set used in training is version tracked, important stuff, so you can compare and you can audit and check the previous versions. Environments, on the other hand, are curated, pre-built by Microsoft. You have multiple different kinds of environments like PyTorch, TensorFlow, whatever is a weapon of your choice. You can even bring your own Docker image or Conda specification. So you will have build up the specific environment with all those references, with all those pip installation that you need to have to run your experiment. This is as well versioned. Every environment changes, create a new version, so you can track through the time that it's reproducible. Same environment, same result. That is important stuff. You can imagine, I believe, from the previous experiences, how many times when you did not have any kind of setup, isolated, standardized environment, that you mentioned the sentence, it's working on my laptop. How come this notebook Jupyter, it's not working on your laptop? Why is that? And stuff like this. It's reproducible, has been said. Shared team members can use identical runtime configurations, and like a lab notebook entry, I use this exact reagents. So think about data assets, connection to the data, environments, standardized, isolated definition of environments where we are going to run our experiments, build our models, etc., etc. Let's do another comparison. You remember on our first session, we talked about Fabric notebooks, and obviously we have it here as well. So let's just compare and connect the dots, when to use in Fabric, when to use in Azure ML. So you will use the Fabric when data is already in one lakehouse. You want to do some kind of quick exploration visualization. You want to have Spark-based distributed processing. You want to be integrated, obviously, with Fabric ecosystem. Maybe team is using Power BI for reporting on top of that, etc., etc. And on the other hand, you will use Azure machine learning when you need systematic experiment tracking, hyperparameter tuning at scale, model deployment to the endpoints. So it's not just playing around with the data and trying to find some kind of correlation with the data and confirm some kind of hypothesis. You want to build up and deploy model as well on top of this. You have responsible AI dashboard. We'll talk about it. ML pipelines for automation of your work, and you have distributed confidential compute in the demand, and you are covered there. Different kinds of scenarios across this. Let's just talk about it. Environmental science, for instance, I'm sure that you will find your example here. Those are some kind of hypothetical scenarios. For environmental science, you can remember our case, predict water quality from sensor data, for instance, detect anomalies in continuous monitoring. You can forecast seasonal pollution patterns, track model accuracy across the region. So we will play around after with our sample data set. Let's talk about biomedical research, biomarker discovery, drug response prediction models, multi-center clinical trial analysis, federated learning for privacy. Let's talk about climate, earth science, climate model ensemble comparison, distributed training on high performance compute clusters, confidential compute for restricted data, etc., 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 etc. So those are just few examples. You can, I'm sure, think of many, 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 many more. But machine learning services are for you here. Okay, we will see this also in action. But let's think in advance. Once when you do your experiment, once when you do the job which is going to train your model, which is going to then test your model, and then after that you have some kind of model that is going to be available and you want to publish it, you have opportunity to compare those models. You need to evaluate those. You need to, say which is better, but not just, by your gut feeling or whatever, but with some kind of statistics. Machine Learning Studio gives you opportunity to do this systematically. So you have Azure ML Foundry sharing model catalog. You can compare models on quality, cost, latency, accuracy. You can filter by task type, classification, regression, etc., etc. You have ML flow comparison views, side-by-side metrics. You will check this later. And in Azure Machine Learning, you can compare custom models the same way. You can pick the right model from your researcher task and the budget. So model benchmarks, there's many different kinds of metrics, quality index, accuracy, uh, cost, coherence, fluency, etc., 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 etc. So it's important here to notice that you are not alone here by examining which model performs better. You don't need to push it into production workloads or to deal with your end clients or your consumers of the model, let's call it like that. You can compare models immediately through the studio without moving forward. Once when you are satisfied, when you are confident with the all metrics, then you can easily publish the new version of the model. Okay, let's talk about the implications. Let's talk about this virtual lab. You have, from this perspective, opportunity to have reproducibility. So every experiment is versioned, exact Python packages on every single environment, data asset, exact data set version, Git integration, code tracking, and everyone can rerun your experiment. Just a few sentences about this data assets and data set version. You are completely aware that data sets are not stale stuff. You are getting the new data maybe every single day, every single minute or whatever, but you need to do some kind of snapshot, and you need to have some kind of single point of truth where you will say, data until this date is going into my training data set. You have complete support here to do this easily from Machine Learning Studio. This is what exact dataset version means. Git integration, code tracking, you're changing the approach. You're playing around. You need to have version controlling. You will not do this on your laptop in some kind of folder and with underscore version 1, version 2, or whatever. You have complete support with the Git for this. Collaboration, you have shared workspace for the team, which gives you opportunity to increase the productivity among the team members, compare experiments across researchers, model registry. You have one source of truth here. You have role-based access control. You can control who can deploy the model, which is important stuff. Who is responsible for training? Who is responsible for administration and connection to the data set? You have lots of different kinds of roles here and granularity, which you can set up among your team, and works across institutions via hub model. So you can connect like in the Foundry or in the Fabric, lots of the different kinds of institutions and their data sets or sub data sets and share those. Compliance, on the other hand, you have complete audit trail for the ethic boards, not just ethic board. If something happens and you want to check what happened and you need to understand who did what, you have responsible AI dashboard for biases. GDPR data stays in your tenant, important stuff. You are the one in the control where you will put your data. It's not flying around. You are the one who are deciding that this data is going to be in Europe, in I don't know, West Europe, data center. You have AI Act, document model decisions, and you can export experiment history for, some kind of reporting or whatever you need to do. So everything is covered from the perspective of Machine Learning Studio. Let's go deeper. Dig deeper into machine learning experiment lifecycle. We are going to some kind of talk about designing experiments through this whole process. ML Flow, what does it stands for? What is it? It's the technology. It's an open source platform for managing the machine learning lifecycle. It's integrated in machine learning, Azure Machine Learning, and in Fabric. You can log parameters like learning rate, batch size, epoch, metrics, accuracy, loss, R squared, custom metrics, artifacts, models, charts, data samples, confusion, matrices. You can compare runs side by side across experiments. You have as well supported underneath model registry with version stage deploy. And you can think of it as some kind of digital lab notebook for machine learning. And this is on the right side, in general, the stuff that I've been said. Machine learning flow, ML flow, tracks parameters, metrics, artifacts, sources, environments, and tags. And what does it brings you? It's going to speed you up in your dealing with your experiments. I will show you later how. Where does machine learning fit in the AI toolkit? You remember our matrix from the session 3, that not every research problem needs machine learning, like prompt engineering, quick node training data is needed, RAG, ground AI in the research documents, we talked about it, fine tuning, we have adapting foundation model to our domain, and we have opportunity here with machine learning to build up custom machine learning. Why? Because we want to have full control. We want to bring our own algorithm. We want to bring our own data. So we're building the model from the scratch. So this is just for some kind of reminder that you don't need to go through this path, through this journey for every single, I would say, challenge to be resolved. This is why we covered lots of different kinds of services which can help you on your journey. So Azure Machine Learning is from the bottom right quadrant. You have fine tuning, you have not just fine tuning, you have complete machine learning, building the models with your data, with your algorithms, and you have full reproducibility. And our session today covers this remaining stuff on top of the AI Foundry and reusing of the existing models over there and AI services that we learned, etc., etc., etc. Okay, let's talk about visualizing experiment results. You have many ways to visualize data in notebooks. So ML Flow logs charts as artifacts along the metrics. Those are some kind of libraries that are included. Matplotlib, Seaborn, everything is supported. You can compare visualizations across the experiment runs. You have auto-generated plots for common machine learning metrics, confusion matrices, different kinds of other aspects. You can export those charts for publications or reports, and every visualization is linked to exact model version, which is really important stuff. Let's now examine the part where we want to train and build our model. So this is some kind of common job that is part of training script, and it's running on the remote compute. So remember, our story about the compute instances, clusters, etc., etc. By this, these few lines of code, you are defining the job that will be run on this compute instance which is provisioned somewhere in Azure. So this can be your Python training code. You are the one who are deciding what is inside. Is it some kind of reference to the PyTorch, TensorFlow, or whatever? You are the one who are referencing the environment. Environment is something that is here predefined already. You will see later how definition of environment looks like. So remember what environment is. It's a complete definition of predefined packages of some kind of all necessary references that are necessary for the running of your algorithm and the training script. Compute, where are you going to run this? Either on cluster, either in some kind of serverless mode. Inputs, data assets. Obviously, we need to have reference to the data. Parameters, it's important for us. And outputs. The name of the train model, metrics, artifacts, where this is going to be. And you can easily then submit this kind of job and monitor. You don't need to keep your laptop open or whatever. This is something that is happening in the cloud on the compute instances that you've been provisioning on. And every run automatically is tracked in the machine learning flow. So here on the right side, you have snippet how this job configuration looks like. Hyperparameter tuning with sweep jobs. You have a possibility to set up systematically search for hypermeter space, grid search. You can try every combination, small spaces, large spaces. You have opportunity to have other stuff as well. Different kinds of search strategies, grid, random, Bayesian, and you can do like with this running hundreds of experiments in parallel. And this is just giving you the great support for using all this cloud power and infrastructure that can be provisioned on the fly and for your particular use cases. AutoML is the one option which you can use here also, which is nothing else but automated model selection. AutoML tests multiple algorithms automatically. You can think of it, that you have some kind of data set. On top of that, you can build up some kind of pipeline that will do what? Some kind of data profiling. It will find out missing values, types, distributions. It will propose some kind of feature engineering. It will propose algorithm selection from it. You have automatic, lots of different kinds of built-in algorithms already there, which are then applied to your data. Why? Because you want to build up some kind of model after it. You have hyperparameter tuning, best parms for algorithm. You can combine top models for accuracy. So your end result can be superposition of the results of the multiple models. And you have evaluation, where you will track some kind of metric, explanation, fairness. Idea is that this is not a black box. Every decision is explainable. It's ideal when you're not sure which algorithm to start with your data exploration. So you can leverage this technology to help you and to speed you out in terms of that. ML pipelines, this is the example how some kind of workflow looks like and what can you achieve with this machine learning services. So all those chains are steps in some kind of automated reproducible machine learning workflows. This is like some kind of research protocol. We are starting with data preparation. After that, feature engineering. After that, we are going in the process of training model. After that, we are evaluating metrics. And we are doing this in cycles until we are satisfied with the matrix. Remember that we can compare different kinds of models. And we are after that registering the model, and we can move it forward and publish it for the customers, for the users to use it, to consume it. Each step is independent. You can rerun failed step, not the whole pipeline. Data flows are typed. You can schedule those pipelines. By mean, why would you want to do that? Maybe you want to do it nightly, retraining of the model with a fresh data set that came up the day before. So you can schedule to that training of the model is run at 3 a.m. and some kind of evaluation and automated test after it. And if everything is okay, you can even push it further and deploy the new version of the model by the morning, fully automated. So you can version the whole pipeline and reproduce any past result. Let's bring back to our test training data set for start. It's European water quality. We have it's a small amount of data, but the principles are the same. Either we're talking about the small amount of data or the big. We have some kind of 508 samples from 8 sites, 9 parameters, 6 years of data from 4 countries. Those are the parameters over there. pH, dissolved oxygen, water temperature, turbidity, nitrate, phosphate, etc., etc., etc. So what we did, and I will show you how, we did machine learning task for demo that I'm going to show you. We want to predict dissolved oxygen concentration from the other 8 parameters. So we put up those kind of stuff into correlation, and I want to build up the model that will give us prediction once one of those parameters change, what will be the value of dissolved oxygen. So this is in general some kind of regression tasks. Our model learns from the relationship between water chemistry, oxygen level, and this is critical for detecting this kind of risk. So let's now dig deeper into machine learning studio. Well, I will show you. Just give me a sec to switch to other screen. Okay. Do you see my browser? All good?
Yeah, all good.
Beautiful, thanks. So this is already provisioned. Machine learning studio portal. Once when you come in, you will end up on you have opportunity to see all your workspaces. This is the workspace that we provisioned already. You remember our talks about the hubs, etc., etc., etc. But let's check our workspace. So here is on the left side, you can see in the navigation lots of the different kinds of stuff. We have home, some kind of model catalog of the models that we can use. You remember the model catalog is the same practically as we have in a Foundry, but with important addition. And with Machine Learning Studio, we can set up our own models and push them in this catalog, so they're available to be used. We are having notebooks, automated ML, designer, prompt flow, data, jobs, components, pipelines, environments, models, etc., etc., etc. Let's now jump to some kind of job that we want to show here for this purpose of our demo. Okay. So before I will just show you in a practice with our data set how this works in general. So this is a Azure Machine Learning Studio, has been said, and let's examine the data in general. Okay, we have already set up the reference to the data. You see here that we have, URI. When I click on this, I downloaded the CSV file, which is in the storage. Let me just, here is downloaded. Okay. So this is our data. It's 508 rows of samples, 8 sites, 9 parameters. It's registered as a version data set. That's our one input for our training. It's important to understand that behind this, we as well have compute. We provisioned the compute instance over here. You can see it. When I click on it, you can see what kind of compute instance is it. We have 4 cores, 14 gigabytes of RAM. We have this amount of disk, etc., etc., etc. This is something that is predefined, and this is something that is installed over there. We have Jupyter Lab, VS Code, terminal notebook. It's created. This is some kind of address which we can get to it. So it's important to understand we are going to use this compute instance for our particular stuff. Okay. So let's just jump to our jobs. Okay. Not here, but here. I already did run multiple different kinds of algorithms. I just wanted to show you that. This is our job that has been run, and with different kinds of parameters and different kinds of algorithms been testing on this data. Okay, you see here different kinds of parameters. You see the result in the metrics like this. You see the status of the job, who did run it. You can see different kinds of metrics. There is some kind of as well images generated here for us for examination to understand if there were some kind of child jobs. You will see it here. You can, if the stuff is complex, you understand that we have multiple different kinds of opportunities to parallelize the stuff. Outputs from this. Okay, this is our model which has been built by the code. This is the conda file, which will then be served as some kind of environment set up for running our model. Requirements. You have as well different kinds of dependencies over here, and this is the binary. This is the model that has been built up. Okay. What is important over here is that we can compare different kinds of runnings with different kinds of algorithms and compare them by standardized metrics. R2 score, okay. R2 score, for instance. Importance, lots of the stuff over here for comparison. Okay. So let's drill down into this one. The best R2, it's this one, job. Don't be confused about this Brave Candle or whatever. Those are some kind of dummy names that Memo Studio is giving, but you have complete opportunity to tackle this and to change this. Okay, this is our general job. And on top of this, I showed you the different kinds of images, and that is giving us some kind of statistics of examining of training data set and evaluation of the data. And we did comparison. And after you're satisfied with some kind of model, this is the one, you have opportunity to register it, which I already did. I won't go through this wizard again. Your model is over here. This is our model, which then you can use it. And you can deploy it in a different kinds of way. You can use it as a real-time endpoint. You can do some kind of batch endpoint. And you can deploy it as a web service. What does it mean? This model is going to then be packaged into the image and deployed into the container with all necessary infrastructure that is needed for running the code inside it and the model. And you will be able to consume this model either from the API, either from the SDK or the CLI. And you can reshare this model with the rest of the consumers, or maybe some kind of quality assurance guys who are going to do some kind of other re-evaluation. Maybe you're going to share it with application developers because they want to reuse your model and want to build up into applications, so application can have some kind of smart processing and consuming of machine learning capabilities. So that's important over here. So every parameter, every metric, every chart, it's versioned and reproducible. This is the standard in general of whole process of connection to the data, from the whole process of exploring the data and do these machine learning activities that you guys do, and all the way to training, retraining, and after deployment and publishing of the model. Okay. So this has already been shown to you. Let's bring back to our PowerPoint. You can see my PowerPoint again? All
Yes,
good?
all good. It works.
Beautiful. Okay. So what we saw in this glimpse, the preview, I understand that there's lots of information for you, and this is the first time you saw this whole ML Studio and everything. But what we saw, we connected machine learning to the data source, which is in the blob storage. And our data source was some kind of dummy CSV file with 508 rows, 9 parameters. We having some kind of Python training script written there. We have different kinds of hyperparameters, learning rate epochs, and we connected and provisioned compute instance, Azure ML cluster. On the output, on the other side, we tracked experiments with full parameter history. We had comparison charts across multiple runs. We have a registered model with version number, and it's reproducible. Anyone can rerun this with the same results. That's important stuff. And can continue work from where you left. You can leave it to the other colleague. You need to remember that every single step that we show is completely configurable from the perspective of security, role-based access. If someone is you're responsible only for the quality of the data set, that will have only permissions to this part of the pipe. If someone is responsible only for the notebook and to exploring the data, understanding the features, understanding the correlations between the data, then you can limit him only to do that. And on top of that, you can limit the guys who are responsible for the training of the data set or the model from the data set. And on top of that, you can limit who is responsible for deployment of the models. And that's important stuff there. And even, provisioning of the compute instances over there, management of those, etc., etc., etc. So you have complete granularity for every single stuff. To recap, every experiment is version record. It's like a lab notebook entry that cannot be lost, overwritten. So founders and ethics boards can audit every model decision through ML flow tracking UI. Okay, let's move forward with some kind of broader picture with research implications. We have some kind of, let's say, fictional, traditional approach where we train model in Jupyter on our machines, on our laptops, where the results are scattered notebooks and which is the best params. Someone is going to say, I think it was this one. Colleague cannot reproduce. Ethics boards can get paragraph without complete journey, without acknowledgement of everything that happened in between. And the model can be lost when laptop crashes. You don't have version of your code. You don't have any kind of stuff. With Azure and machine learning workflow, you are submitting job to managed compute. It's running in the cloud. You track everything, every single run, params metrics. You have best params identified automatically. Anyone can rerun this with a click. Ethic boards can have full audit log, and models registered are end version. What is the impact? Peer reviews, verify your results. Founders can see rigorous methodology. Collaborators build on your work. You can years later have exact reproduction. You can publish experiment records, and you're moving from it works to here is the proof. You have complete platform that are supporting you in this journey. Let's move forward and talk about distribute and confidential machine learning patterns. Let's think about one fictive scenario where we have multi-center clinical trial, and this guy, Dr. Martin, has this kind of challenge, I would say. So he said, we have patient data from 5 hospitals across 3 countries for cancer biomarker study. Each hospital has its own ethics approval. None of them can share off patient data. We need a model trained on all 5 data sets to have statistical power. How do we train a shared model without any hospital seeing other hospital patients? This is the real life scenario, and we can, talk about this in terms of the sharing and collaboration between institutions and doing on some kind of collaborative challenges together. So we have 3 options. We have federated learning. Each hospital trains locally, shares only model updates. We have confidential compute. All data is encrypted. Azure cannot see it. You have your own key bring up for encryption of the data. And you have as well something that is called Arc, Azure Arc. We are not going to dig deeper into this technology, but you have Arc-enabled machine learning, where compute runs on hospital infrastructure and Azure orchestrates. So you have orchestrator of all this training process, which lives in the Azure, and all data is in the different kinds of institutions. And you have everything connected through this. So federated learning, confidential compute together are providing the strongest guarantees over here. Azure Confidential Computing for machine learning is solving the problem where cloud provider could theoretically access data during the process. So you have here something that we mentioned, trusted execution environments. What does it mean? It's hardware enforced isolation. Azure operators cannot see that data. So you have confidential virtual machines, confidential GPUs, and data is encrypted in a memory during training. So it's bringing you lots of advancements and solutions to protect the data and to hold your flow. So it's ideal for health data, genetic research, regulatory clinical trials, all those highly sensitive, I would say, scenarios. So you have protection layers. At the rest, it's encrypted on a disk in transit. It's encrypted over network with the protocols which are standards, and in use, it's encrypted in a memory. So Azure Confidential Computing, it's bringing you completely protection of data in 3 states: in use, in transit, and its rest. So keep in mind that you will have opportunity to do this as well. Arc enabled machine learning, data stays local. So nothing is encrypted, nothing is moving to the Azure. Your data stays in your local data center and you can use it. Why? Because it's okay, it's fine with you, and it's not any more question why, it's a question how. So you have this technology called Azure Arc. What does it mean? It's connecting on-premise Kubernetes cluster to Azure ML. So data never leaves your institution. Azure orchestrates job. It compute runs locally on the locally Kubernetes. IT manages Kubernetes, so your internal IT can manage Kubernetes clusters. Researchers are using Azure ML Studio. Why? Because you have orchestration over there. You don't care about the infrastructure and this kind of stuff. You're focused only on your job, how to achieve the best results from this data, and how to train the best possible model. Same SDK, same tracking, same model registry. You are using existing GPU investments on-prem. You are not, throwing all your investments from on-prem institutions in a garbage. You can then play around and have hybrid patterns, train locally, deploy in the cloud, either way around. So on the right side, you can see some kind of diagram describing this. In the cloud, you have machine learning workspace, registry, ML flow tracking, monitoring, and in your institution, you have K8 Kubernetes cluster, which is connected via Arc to the cloud. GPU, there you have your own infrastructure, GPU nodes, training jobs, research data. So idea is that data never crosses the boundary. It stays in your institution, and orchestration is in the Azure. Federated learning, it's collaborative without sharing the data. So the same approach as we described already. We have multiple institutions are training the shared model. They are collaborating on some kind of building their own product together. Raw data never leaves any institution. Each site is training locally, sends only model updates. Central aggregator combines updates into global model. So maybe you are just training on the particular subset of the data and you want to merge this. Confidential computing enhances security. Aggregator runs in memory, in use cases, multi-central clinical trials, cross-border environmental monitoring, GDPR compliant by design. And important stuff here is Azure is providing the infrastructure, you're defining protocol. Here on the right side, you can see some kind of fictive topology diagram for this particular case. Netherlands, Germany, Denmark, which are all collaborating together on resolving of one challenge. So final model benefits from all institution data in general. This is some kind of matrix, which pattern fits your research from the perspective of different kinds of, I would say, views, data location, who computes, trust, best, complexity, GDPR fit. So you have a solution of confidential compute, Arc-enabled and federated learning. I will not go through any through all of those stuff, just remember that this is some kind of recommendation matrix for you to decide. But the key takeaway here is that you are not alone. If your question in your head was, I have invested in my infrastructure, I have really good setup in my data, and I want to use my infrastructure and I want to keep my data inside my institution, you have opportunity to do that and to leverage all those nice features from the Azure and to do some kind of hybrid approach and whatever crosses your mind. Okay, those are some kind of implications. For health research, for instance, patient data never leaves hospital. Ethics board approval is simplified. Multi-center studies are now possible from this perspective. Genetics data stays with institution. Earth science, for instance, satellite data processed at the source. National security data stays local. Cross-border collaboration enabled. We have UNESCO protected site data secured and real-time sensor data processing. Social science, survey, privacy guaranteed. Cross-national panel studies feasible, researchers cannot see individual records, etc., etc., etc. Only aggregate model can be shared. And I'm sure that you can think of lots of different kinds of solutions here as well. Let's go into demo mode again and to think about it and to show you one more cool feature, which is called responsible AI dashboard. Let me again change my okay. Can you see my screen?
Yes, now we can see.
Okay, beautiful. So I'm going to show you how Azure machine learning goes beyond accuracy and expecting model for fairness, errors, and interpretability. I will show you something that is called responsible AI. When you open the model, you remember from the last demo that we have here support for different kinds of versions of the model, some kind of artifacts, what is in this model, endpoints if the model was deployed, what kind of jobs, what kind of data is behind, etc., etc. But important here is that we have responsible AI support. What does it mean? This is the feature that gives us interface that makes responsible machine learning engineering efficient and in general to understand what is happening with our model. So this is the pipeline job that analyzes our model across multiple dimensions. And I'm going to show you how this job looks like. I already created it. If I go on a create, I will need to go to this wizard that is going to help me to achieve this, to speed up the things. I already did that. Just give me a sec. This is our job. Let me just show you how this thing looks like once when you create it. Okay. And I'm going to explain you what do you see over here. So look at this pipeline and the model and our test train and the test data sets are flowing into constructor, which then runs for parallel analysis. We have causal effects, we have counterfactuals, error analysis, and feature explanations. And results are gathered into a single dashboard. Okay, so what does it mean? Our model is going to be tested against this, and we are going to have some kind of dashboard, and we are going to have some kind of analysis about this. Let me just spare a few sentences and just explain this error analysis. So error analysis in general, here it is. It's a building decision tree where the model fails. For our water quality model, it would identify that predictions are less accurate at the sites with very high turbidity or extreme temperatures. And in general, this tells us where to collect more training data. Feature importance. Where is the feature importance? Okay. It's we already saw the in general, this is giving local explanations why the model made this specific prediction for this specific sample. So global importance tells us either overall, some kind of overall drivers, and the local importance tells why this particular reading was flagged. Counterfactuals is giving us answer what would need to change for the prediction to be different. For sample predicted 6 milligrams of liter dissolved oxygen below the healthy threshold. Dashboard shows that reducing water temperature by 3 degrees would push the prediction to 8, etc., 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 etc. So what I'm trying to say that you have different kinds of options here, what to push here to test your model against the training testing data sets. And in general, this dashboard is really cool feature which can gives us hidden failure modes. Feature importance builds trust. Contextual counterfactual make the model's logic tangible. Some kind of PDF scorecards gives ethics board evidence that we need. And in general, this dashboard needs 15 to 20 minutes to be generated, the structure. So I showed you the pipeline in the background, what is happening and across that. So you will then have everything, really nice shown and to understand the quality, let's say, of your model. So 500 samples, 8 sites, 9 parameters, 6 years, 4 countries. We have, in the previous example, 3 models compared: random forest, gradient, boosting linear regression, top features which we excluded, and healthy dissolved oxygen. And we have this pipeline, which is testing our model through the 4 components. That's important stuff to understand here. Okay. Let's bring back to our slide again. And let's just mention what is able to see on the dashboard in general. You guys, can you see my presentation?
Yes, we see the slides now.
Beautiful, thanks. So we have error analysis, some kind of cohorts, higher error rate, identifying systematic failure patterns, decision tree, error distributions. From interpretability, we have global feature importance, local explanations, visualizations, fairness, comparing performance across groups, detect some kind of impact, selection rate analysis. Beyond accuracy, model that is accurate but unfair is not ready for the deployment. We can map, identify potential harms before building. We can measure those harms and test for biases, errors, edge cases. We can mitigate the content filters, fairness constraints. We can manage, we can monitor stuff in the production and retrain when needed. And this is important because we are under AI Act in the European Union. and transparency and documentation is required. So with this, you have opportunity to generate lots of the audits and lots of the additional testing and evaluation stuff from the perspective of your model, from safety systems, system message grounding, user experience in general. Content safety layers, few words about this and why is this important. You are already familiar with this from our session with AI Foundry and consuming of some kind of foundation LLMs, which has this content filters. Same thing applies for the models that we are building with Machine Learning Studio. We need to obviously think about the safety layers. So content filters are protecting model inputs and outputs in general. In our demonstration, we have been playing around some kind of numbers, but you can understand it, and you probably are doing some kind of models that are not just related to the forecasting or stuff like this. We want to avoid violence, hate, sexual content, self-harm categories. We want to have configurable severity threshold for every category, prompt shields that are preventing jailbreak attacks if we are doing this kind of inputs in our models. We can protect against misuse of training models, and Azure ML and Foundry are sharing the same safety infrastructure. This is important to understand, and you can document safety the configuration for compliance. So filtering input and output using thresholds, violence, hate, sexual content, self-harm. Responsible AI in practice. So we had some kind of error tree, feature importance, fairness, counterfactuals. What is the value of this? Ethic boards can review model behavior before deployment. PDF scorecards is shareable. It's a non-technical summary. It identifies bias before it affects research conclusions. And this stuff aligns with European Union AI Act transparency requirements. Once when we got our model trained, working, it's responsible, it has really cool content filters and everything, and we are happy with this, we need to think about deployment. I showed you some kind of options in a previous, in a first demo of today's session, but let's explore the full pipe from notebook to production endpoint. Real-time batch endpoints. What is managed online endpoint? It's a real-time predictions by REST APIs. That means that your model is going to be wrapped up, built up in some kind of container, and is going to be accessible through the API, to the REST API. You will be able to consume this model, send some kind of input, and getting outputs. What is cool stuff regarding this? You have support for infrastructure, auto-scaling based on the demand. Why is this important? Maybe you push this model to live, and as been said, some kind of application development team is going to consume this, and they're going to play around with this kind of model in the some kind of testing environment, and they're going to release the production version, and in one day, I don't know, 50 people is going to consume this model through the application, and next day 500,000 people. Of course, overload is not the same. We need to have infrastructure that is breathing, that is extending itself. This is auto-scaling, giving you opportunity here, and the whole infrastructure in the back. So blue-green deployment, safe updates, it's built-in, it has built-in monitoring and logging, some kind of use cases, real-time water quality alerts, field instrument calibration. On the other hand, batch endpoint gives you opportunity to process a large data set asynchronously. You can schedule scoring jobs daily, weekly, or whatever that is, multiple times per day. It's cost efficient. You can compute scales to zero. So when you use this, and when you're finished with a job, it's going to immediately go to zero, so you're not going to be charged about anything. It's important that You have parallel processing across partitions. Why is this good? Maybe you have monthly sample batch analysis. Maybe you have retrospective data scoring or stuff like this. Context for you guys, most researchers are starting with the batch endpoints. Those are processed accumulated samples, and then adding real-time endpoints when they need instant predictions in the field. That's important stuff. Deployment options compared. Okay, you have some kind of table here, metrics with standard deployment, serverless compute, managed compute. We already talked about it, but it's worth to mention already that everything is managed online, and Azure handles scaling, monitoring, networking, Kubernetes endpoint. You can deploy your own Arc-enabled cluster. You don't need to use machine learning provisioned Kubernetes cluster, which is in the background. You can bring your own. You have batch endpoints, schedule scoring, accumulated data sets, serverless token-based billing, no infrastructure management. You have blue-green deployment. You can update models without downtime. You can choose based on latency needs, cost model, and data location. Okay. Scenario. Deploying our water quality model. Let's go further from the training. You remember the whole pipe here. You have training step. After that, you have registration of the model. After that, you have deployment, batch endpoint, or maybe some kind of real-time monitoring. Why is monitoring important? Why? Because you want to learn something from this. You want to learn if there's some kind of data drift alerts when the distribution shift or something like that. And based on that, you want to retrain your model, and you can fully automate this kind of stuff. You can fully automate pipeline to do this process continuously, and this is those stuff is being done in modern teams. So, from perspective of our fictive character Elena, she has deployment plan. She's going to collect new samples from 8 monitoring sites every month. Our batch endpoint scores all new samples automatically. When seasonal changes cause the input distribution to shift, for instance, summer, algae blooms, or whatever, monitoring system detects data drift and triggers the retraining pipeline automatically. So Elena then received alert and reviews the new model before it replaces the old one, by republishing the new version of the model. So every single thing from this stages, all those stages can be fully automated. Monitoring deployed models. You have data drift, input distribution, model drift, prediction degrade as the world changes. That's something that is obvious. Monitoring can detect both automatically and alert you when retraining is needed. So you can then connect to this event and start automatically retraining, or go into some kind of depth, deeper analysis for it. Important to remember that without this monitoring, models predictions silently degrade. We don't want to be in a position to wait that the end consumers of that model gives us the info that model is not performing good anymore. Okay. Moving forward, let's wrap and close the loop, complete loop, from experiment to production. Let's wrap up all the sessions, workshops that we have. Let's talk about the full landscape. As been explained on the last sessions already, you don't need to think about consuming of just one technology, and you're not limited to that. Full power is getting of connecting those technologies and understanding which technology serves us the best for which case. Fabric. Data lives in one lake, ML flow tracks notebooks. We can use Spark clusters for distribution preparation, Delta tables as Delta sources, data agent for exploration. On top of that, we have Azure machine learning. Why? Because we want to leverage the systematic experiment tracking. We want to have hypermeter tuning. We want to have some kind of responsible AI dashboard, model registry deployment. We want to have opportunity to monitor in retrain. And on top of that, we can use the Foundry, where AI agents can call deployed models. We can then build up the AI agents, full orchestrations and everything there. We can have on the Foundry code interpreter for analysis. I believe, guys, you remember that continuity interpreter gives us opportunity to execute Python code in isolated environment, and that AI agent can consume this. RAG over research documents, content filter safety, and EU data resistancy controls. So from your perspective, the full power lies in a combination of everything. For you guys who wants to dig deeper into those technologies, in general, there is lots of some kind of Microsoft Learn paths and lots of certification paths. So you can go deeper in it. You can just Google for those are the codes for those certificates on the Microsoft Learn platform. So you have DP 3007, applied skills, train and deploy, machine learning. You can go for machine learning engineer associate, go for Azure data scientist associate. On the AI development path, AI apps agent developer that is coming up, AI 200, AI cloud developer. And if you want to, understand Azure AI fundamentals and all this stuff in general better, if this is too abstract for you from this couple of sessions that we went through it, and there was lots of information, you can go on the entry level and understand the Azure AI fundamentals in general. So recommendation for you guys is to start with applied skills. Difference between applied skills and certificates. Applied skills are covering just one aspect of the whole journey for getting the certification from Microsoft, and applied skills give you opportunity to play around with the technology in some sandboxes to feel how it's like to deal with this. So start with this, and after that, go in an AI 300 and just start playing with this technology, leverage every kind of possibilities from this. Lots of hands-on lab exercises. I know it's hard to understand from just my demos what is happening. You need to feel the technology. You need to be able to play around with it. So you can go to the DP 3007, where you will be able to explore ML workspace, data available, work with compute, run training scripts, track ML flow, deploy to the endpoint. You can reuse already been given some kind of references to the GitHub official Microsoft repositories, where you can reuse some kind of labs and to play around with training and tracking of machine learning models in a Fabric. And you have some kind of diabetes data set to play around, data science end-to-end in Fabric. On ML ops stuff, this is where true power lies in terms of full automation of the whole workflow, end-to-end ML ops challenges. So CI/CD for ML models. This is related to the whole completed automated pipeline, when on the certain event of the monitoring, you start to retrain your model or redeploy new version of model, stuff like this. Integration with GitHub Actions, model deployment automation, etc., etc., etc. Few more sentences to wrap up all 5 of our sessions, the complete ML research infrastructure on Azure. So what we did in our 10 hours journey, let's say it like that, we started by observing data platform solutions. OneLake, Lakehouse, Medallion, Gen2, Spark. After that, we went into exploring of some kind of AI services, Foundry agents, language search, document intelligence, machine learning platform today, Azure machine learning, ML flow experiments, pipelines, dashboards, dashboards. We covered as well how to deploy this online endpoints, batch endpoints, monitoring, drift detection. As well, we talked about from the AI services, how can you consume a redeployed model through those APIs, through these endpoints, talking about language search, document intelligence as well. And what is important stuff, everything is covered here with the governance layer, where you have purview, where you have covered GDPR, AI Act stuff, confidential compute, and ARC in some kind of workloads where you want to consume your existing infrastructure and you don't want to send any kind of data to the Azure for some kind of reason, you have everything covered here. Lots of information, lots of stuff, lots of dots where you need to put your focus on, and you need to see from which you can benefit on the best. So in this 10 hours, we just went through the sneak preview of it, just explaining what kind of challenges are you experiencing in your everyday workloads, and what are the answers in an Azure ecosystem for that, and what kind of platform maturity can you use to help you to be more productive, efficient, to have better collaboration, traceability, explainability, governance, and everything. Okay, those are some kind of statistics. Machine learning for research by the numbers already been mentioned, but we have more than 11,000 different kinds of models in Azure Model Catalog. You have 60 days free Fabric trial for researchers, which you can play around with it. You can, if your institution does not have already, you can ask for $5,000 for research to play around with the technologies. And you have different kinds of layers for data protection, REST, transist used. So Azure Machine Learning Fabric, AI Foundry together are providing, enterprise-grade machine learning infrastructure at research-friendly, I would say, pricing. But it's important for your perspective to understand that there is no challenge which you cannot achieve with this platform. Next steps. Here are some kind of materials, some kind of learning paths already been mentioned, where you can check for the Fabric trial, for the research credits, documentation, etc., etc., etc. Combine this with the materials that I sent to you, that I already mentioned in the previous sessions. So combine those kind of stuff. And series is complete. So what can you do now? You can set up the Fabric workspace with Lakehouse and Medallion infrastructure architecture for your research data. You can build reproducible data pipelines with data flow, move data, do the data massage, full ETL process, do some kind of stuff with Spark notebooks, and do ML flow tracking. On top of that, you can set up different kinds of AI workflows, maybe deploy different kinds of models in AI Foundry, play around with, I don't know, Opus 4.8, comparing with GPT-5.5, comparing with Microsoft new models, or maybe your own model there. You can design prompts, build AI agents with code interpreter easily. You can even in an AI Foundry build up complex orchestrators with Microsoft Agent Framework on top of this. On AI services, you can connect to some kind of pre-built services which are instant ready for consuming. You can do some kind of customizations, talking about text analytics, knowledge mining, document intelligence, and research documents. You remember that we talked about in the last time of the vector databases, vector search, semantic search, etc., which is really beneficial for a large amount of data and do some kind of semantic search all over it. RAG patterns, etc. And if this is not enough for you, you can go into experimental design and run machine learning experiments with tracking, tuning, dashboards, confidential compute, go all the way from connection to your data set into process of training data, testing models, training models, testing models, publishing models, do some kind of batch consumption or exposing those models for integration for some kind of applications, etc., and automate the full flow of it. So lots of the stuff which can be done right now, and all this completely auditable, traceable, governance on the each step, and everybody in a whole ecosystem is going to be happy about it. Having that said, I would like to ask you if there are some kind of questions. I'm open to questions, not just related to this session, but in general, whole series. Looking forward to hear you about this. So please go ahead.
Meanwhile, I would like to thank you, Mario, for the great session. And I mean, I'm personally very far from being an expert on the topic, but I found this session very interesting as well, and especially to understand the wide range of possibilities from my perspective. I mean, of course, I would like to remind everyone that as Mario is sharing his email, um, I mean, he can also reply to questions based on that. Meanwhile, I'm reminding that the recordings of the previous sessions are already available via the GÉANT YouTube channel, and the recordings of this session will be also available soon. So just giving one moment more for questions.
Sure. In general, here is my contact, and I would be happy to answer. And you can find me on a LinkedIn as well. If there's some kind of question occurred, I will be happy to answer it for sure after this session as well.
Great, thank you. And unless there are any more questions, I would also like to thank you again on behalf of our community for the great series of workshops. And again, reminding that the full series will be also available in recorded format. Thanks again.
Thank you, Leonardo. Thank you, guys. Greetings from Croatia, seaside.
Thank you again. Bye.
Bye-bye.